Hello, on February the 8th. All right, let's do this. Let's turn off these. All right, largest divisible subset. Given a set of distinct positive integers, nums, return the largest subset answer such that every pair of elements in this subset satisfies. They're divisible. If there are multiple solutions, return any one of them. All right, we want to return the largest subset. The largest. All right, the largest subset such that every value within it are divisible. Okay. We can sort numbers first. So if we go left to right, we only need to consider the bigger one divisible by the smaller one. All right. And then as we go through them one by one, okay, we can go through this one, and then we can see if it's divisible. You know what? That's probably gonna be DP. I mean, it's asking for largest, so maybe binary search will work as well. Actually, how are you gonna do binary search? I don't think so. Let's go DP idea. So DP, I have something, 0, 1, 2, 3, whatever, right? Let's say we know the largest, but you asked me to return the largest subset. That's okay. Okay, let's say I know the largest subset of this. Okay, I know it. The largest subset. It's divisible, right? It has to be divisible. It has to be divisible. Because you can have multiple, right, given the current. And then the new one coming in, and the new one coming in. How do I know where the new one belongs? So the new one can belong to different depending on what the new one consists of, right? The new one can belong to one group or it can belong to the other group. Graph. If it's divisible, we have a link, and we just want to find a path where the longest path. I mean, every 2 has to be. So if it's a path, right? Yeah, if A is divisible by B and B is divisible by C, then A definitely is divisible by C, right? That's correct. So if we have a divisible subset, then we can definitely form a path among them. Yeah. Okay. So, okay, we run O(n) squared, so we can build a graph. Once we build a graph, how do we find the longest path in the graph? We start from something, right? Now we start going until cannot go, or either until we cannot go or until we get back. Or maybe let's make it not bidirectional. Make it into like a tree, right? You can only go small, only small link to big. Only small value link to big value. Small value link to big value. Yeah, because we want a path. We want a path. So we start from the smallest, try to find all the other, right? We'll find the smallest, and we try to find all the other that can divide it. So 1 can link to everything, right? In this case, if we go 1 to 3, so 1 can go to 2, 1 can go to 3. Or 1, 2, 3, 4. Let's do 1, 2, 3, 4. 1, 2, 4, 8. Yeah, this is actually a good example. 1, 2, 4, and 8, right? So we say 1 can go to 2, 1 can go to 4, 1 can go to 8. Now 2 to go to 4, 2 can go to 8. And then 4 can go to 8. So it's like this, right? It's like this. And we always start from 1. So 1 go to 2, 1 go to 4. So I have 1, 2, 4. I don't go back, right? The path doesn't go back. So from 4, I can only go to 8. And 8, nowhere to go. So I have 1, 2, 4, 8. 1, of course, I can go to 4, I can go to 8. Right? Or 1 can go directly to 8. Will we have a situation like this? Will this one happen, right? We will start from here. Oh, we start from here, yeah. But if we start from here, we definitely get a chance to go through the whole thing. But will we, like we start from here, we go down to this one. All right. And then here I can go this, 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 or I can go this, this, this. Are we duplicating? Right, this is what I'm worried about. We might be duplicating the situations. Yeah, I can see this one happening. Or I can be 1, 2, 4, 8. Actually, that's not gonna happen, because if we make the path directional, only small point into big, right? So if I this point into this, if this point into this, and this point into this, these two can only have 1 point, which means if I go this, 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 right, that, 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 we're done. Or we go that, that, then we cannot keep going. Maybe. Let's give this a shot. Let's give this a shot. Let's turn this into a graph and see how that goes. Okay, and the graph has to have strict, we say, must be small leading to big, right? Must be small leading to big. Okay, so first of all, we say arrays dot sort nums. Okay, Now after we sort it, we need to build the graph. We use a hash map. Yeah, we use a hash map to build a graph. Okay, so we say map to integer with a list of integer. Okay, we say this adjacency. I can call it matrix. Graph hash map. Okay, and then that will take O(n) squared to build it. Ugh. Okay, that's fine. So for int I 0, okay, I smaller than nums are length, I plus plus, okay, and for int j equal to I plus 1, j smaller than nums are length, j plus plus, okay, and they're all distinct. Okay, so we just say if nums j mod nums I is equal to 0, then we do, what do? We do graph dot put if absent. So we start from I, right? This one should be new array list. Okay, new array list. And then we say graph dot get nums I dot add nums j, right? Ugh. Okay, so that's that. So with this, we build a graph. Now after we build a graph, we need to DFS the thing and then find the largest, right? We find the largest. Okay, so what are we going to call it? We're gonna call it the largest. It's gonna be a set. Okay, we're gonna use a set. So set of integer. Wait, what? What happened? It just disappeared. Recover. I have no clue. I don't know which key I press. Okay, let me just save it. I have no idea which key I press, and then it just disappeared. Wow. Okay, this is gonna be the largest max path. Okay. And yeah, we're gonna save the max path, and we're gonna say private. It's backtrack. It's called DFS, right? It's a DFS with backtrack void DFS. I don't think we're gonna return anything. We need a node. Node is gonna be an integer, right? Oh, we need. All right. I'm sorry. This one has to be dd, and we're gonna paste this one here. Yeah, unfortunately, graph has to be here because I need to use the graph here. We also need path, right? So we need a set integer path. Okay. All right. So what do? We hit the current node. We have a path coming in, right? We have a path coming in, and we hit the current node. Then we try to move on to the next node, right? We try to move on to the next node based on the graph. And whenever it's done, okay, so it'll be like this: for int child graph.get node. Ooh, what if it doesn't have? What if it have get or default? Get or default. Okay, so if it doesn't have, can I say empty list? I forgot. How do we do empty list? Empty array list. How do I do that? now is empty. Empty array list. I think I can just do... That's not what I want. I want... Yeah, I can just do a new, right? It should be fine. But I remember there are collections that is already just empty. Right? There should be a... It's not too empty. How tell me? Create empty list. Yes, there is an empty list. Collection of empty lists and a new list is immutability. Returns a list that cannot be modified. When creating a new list instance, you can modify it. Okay, so I'd like to call this, how do I call it? Collections dot. So I can say collections dot empty list. Nice. Okay, so that's what I want. I want an empty... What I'm not doing is for child this. Okay, so for each child, right, I probably need to add a path to it. Okay, so we should say path dot add node. Okay, so a path add a current node, and then for each one I'm gonna call it DFS. or if child is not in node, so node dot contains, not path dot contains child. So if it does not contain, right, if it does not contain, then we call DFS child path, right? And then we go through blah blah blah. Once we finish everything, then we need to check if if what? If path dot size is larger than max path dot size, right? If that's true, how do I copy? How do I make a copy? I can shallow copy, it's fine. Copy a set. Copying set. Old set. Another way is to use a copy constructor. Okay, so we can use a copy constructor, or okay, I'm gonna just use a copy. I cannot. Can I use a copy? Yes, I can. Right? I can say max path equal to new hash set. Right? New hash set, and I put path in it. Right? And then once I'm done, path dot remove node. Guess is what's it called? Backtracking. This is backtracking. So we blah blah blah. The method. Wait, what is this? The method from type solution. How do I read the entire thing? Jesus. Okay. It's never used locally. Okay, that's fine. I'll use it locally. Don't worry about it. Okay, so I have this. Then I'll call DFS, right? DFS node. I'll start from nums 0, right? We start from here, and the path is going to be a new hash set. Okay. Once we're done, we'll get the max path. Right, we'll get a max path, and I just need to turn that into a list. I am guessing we can do this. Return new array list, and I'm guessing I can do max path here. Okay, let's give this a shot. See if it's right. Are you correct? if not max path or All right, how about this? If max path is equal to null. Come on, you gotta do. Okay, looks good. I'm gonna just guess that this is the correct solution. So create a directed graph, okay, where each smaller number points to a bigger number that divides it. Then we DFS the graph to find the longest path. O(n) squared, because we need to create O(n) squared to create the graph in the first place. All right, let's see. Come on, is this right? Is right? Ooh, it is not. Oh shoot! Oh shoot! I think we have to go through every single one of them. Okay, I see. I see. Okay. Okie dokie. Okay, so basically you're telling me I'll do this for int node of nums. I do node. Actually, if it's already, because it goes small to big, right? If it goes small to big, so I think if it goes small to big, I always say if node, if it doesn't contain, right? If the max path dot contains, if it does not contain node, then we do it. So we can save some. If it does not contain a node, then we can. If it contains the node, that means we already handled it, and it will never be bigger, right? It will never be bigger. So if it does not contain a node, then we don't do it. We probably, so we have the max path. We probably should say visited. What do you think? Maybe we should have a visited. Visited. Yeah, that means you already visited it. Okay. We have a max path. We have a set of integer. Let's say visited, right? So if visited dot contains child, then we do it, right? Path dot do it and visited dot add. No. Oh, then path doesn't have to be. Path can be a list, right? Path can be a list. Visited is a set, so both add. Then we'll get a path down. That's fine. And if max path is not and path dot size is larger than, then max path is gonna be array list, right? And then path dot pop, I think, right? Path dot pop. Okay, and here I'm gonna do every time it's not a hash set, new array list, right? And then it's not max path, this is visited. And then we're just gonna return max path. All right, let's take a look. Is this one correct? Okay, it's a capitalized letter. Ah, all right, we'll wait. We'll wait. We'll wait. Oh, that's not set. That's a list. Cannot find symbol. Path. What do you mean? What the hell? Hold on. This is weird. Is it right? We have max path, we have visited, we have everything else, and then path add, visited add, we go through everybody. If it does not contain the child, we do the child, we do the path, and then max path or path.size is larger than max path.size, and max path go to this, and then I say I do this. I don't see any problem. Cannot find simple. Oh, there's no pop? Wait, what? Holy crap. It does not have a pop. You gotta be kidding me. Array list pop last. Oh my god. Remove last? Do I have remove last? We do. Remove? No, we don't have remove last. I'm not using Java 21. I think this is Java 6.17. Alright, it has to be remove. Oh, that's so stupid. Remove path.size -1. That's fine. It's just different APIs. I mean, we can handle it, can we? We can handle it. We can handle it. Alright, have the same visited equal to null, or which is the same as here. I should say same if visited. Why don't you just, it's an easy new hash set, right? You don't have to worry about anything. You don't have to do this. You don't have to. Alright, visit equal to contains, and then this we don't have to do this either. If it not contains, right? Does not contain. If it does not contain. Alright, so it goes through this. Alright, let's try it again. Oh, okay. Now we have a real issue. Now we have a real issue. Expected. Oh, because I said it does not contain. So I get 590. So when I start from 9. I think. Yeah, that's a good test case. So 5, we go through everything, right? But then we start from 9, and we'll hit something that's been hit before. That changes everything. That changes everything. I think we have to go back to the previous idea. I think we have to go back to the previous. I have to use max path again. So it's just saying on the current path if it's not visited, right? Yeah. But I also want to not. Yeah, but the ones visited before we have to go. Okay. All right. I don't think this. I have to do this. So let me do this. So we do set. Okay. We don't do this. Okay. And then it's just if the current path, right? So we path will do set as well. Don't do this. So yeah, just the current path. The current path is not contains. We keep going, and then if this, and we don't do array list, it's gonna be a hash set, right? Actually, it max path. No, let's do a hash set, and this is just going to be. This one just going to be the current node, right? We remove this and then blah blah blah. This is the same, and this is gonna be the max path, right? If the max path does not, I probably can say max path is equal to null, or right, max path does not contain. Then we do. This is gonna be a hash set. Right, then we do this, and we're gonna return with a new array list max path. So by doing this, we are guaranteed that each time when we get a new one, we will go through the whole thing. Okay, that's what we can guarantee, and we also kind of save time on the other ones as well. All right, let's take a look at this one. Alright, this is all right. Alright, try one more time. Nope. Nope. What the hell is this? Alright, we're wasting a lot of time. Okay, we're wasting a lot of time. We're duplicating, and I can see that. So maybe, all right, we still need a visited. Okay, we still need a visited, and the visited only handling here if a node has been inside the visited. We don't do it from scratch. Okay, so here is a new idea. We still need a path to be a set, and we need a visited to be a set. Visited to be a set. Okay, so every time we do visited dot add node as well, but we do not check. Okay, we do not check visited here. We will check visited at the bottom. So we'll check visited here. We say visited dot, right? What did you do? I pressed some wrong button again. I always press wrong button. That's been my bottleneck at the moment. Like, I don't press the right button. So here I check on the visited, right? If the current node, if I want to use it to the start, has not been visited, I'll always visit it. And then when I visit it, I'll use a fresh path. Okay, I'll use a fresh path. Okay, so new one. Let's copy this, put it here, run it. Let's see. Come on. Hash set. My bad. All right, try it again. No way. That was still bad. How? That doesn't make any sense. All right, let's try. All right, hold on. Alright, let's keep working on this. What is the problem, man? I have gone through everything. Okay, let's delete this. Are these correct? These are correct, but that one does not fly. When I have a set called visited, which means when we start from the beginning, everything I visited, right? Everything I visited. Because I call visited.add node. And if path doesn't contain, I'll do it, right? Which means if I start from something, and then I'll do something, and then we'll go through a giant path, right? We'll get a giant path. And then when I hit those, right? When I hit those, if it contains the node, then I don't do it, right? I don't do it. And when I hit something, that will always be the first time that those paths gets go. Oh, but then I hit something. Oh. Do I need to use visited here? What do you think? Yeah, I'm thinking. So, like branch, right? You start from something and I branch out. And then as I go a path, right? I go one path down and I hit something else and I go another path down. So maybe that's where the DP is. You need to record the longest path starting from something, right? Yes, the longest path starting from something. If you have the longest path starting from something, then the next time when you hit that, you don't have to go through that again. That's an interesting thought. That is an interesting thought. That is a very interesting thought. So I can simply go through. Okay, so I think I need to change the code completely. So instead of doing this, we're gonna have a memo, right? I'm not sure, but let's try this. So this is a graph and a map. Let's say integer list integer memo. Okay, that's for the memo purpose. No hash map. Okay, so we still need a path, right? We need a path. So let's say we need a path, and the first thing is we check, right? We say if, and this is not going to be this anymore. This is going to be a list of integer. This is the longest. Yeah, this is going to be, oh, why did you delete? I deleted the wrong thing, man. Private. So if, let's say memo dot contains key node, right? Then I just return memo.get node. Boom, done. If memo does not contain, right? If memo does not contain a current, then we need to try the current. Actually, we probably don't even need this, right? If a memo doesn't contain a node, okay, I go through everything and I try to find all there, and I will put myself in. Oh, I put myself in front. That actually doesn't matter, because it didn't really say you have to return a certain order. Right? It doesn't really matter. I can put at the end. Okay, then I simply say. So I don't need these two, right? So for child, then I simply, you know, DFS, right? When DFS child, and this will give me, I need a current, right? So I can say memo.put node new hash, no, new array list, okay? And then this will be list integer path equal to DFS child, right? This will give me a path from child to the end, right? And then we say we want to find the longest, right? So if actually we don't even need, I do need this, right? So we can say if path.size is larger than memo.get node.size, then we say memo.put node path, okay? And then blah 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 blah, at the end I will do memo.get node.add node, right? We put a node and I do return memo.get node. Do I need to create a new one? Because I have a new one here, right? And then I will have put, we get a new path, right? We get a new path here. We do get a new path. We do get a new path, right? We constantly get a new path. Yeah, no. Let me redo this. I don't like it. I will do a list integer res, okay? And then we say res is equal to null or path of size, and then we're gonna do res.size. Then we will say res will equal to path, right? That's fine. And then at the end, we'll say dot put node dot put node new array list, right? New array list res, right? And then return this. May not have been initialized. Ah, screw you. New array list. Then I don't need this. Okay, so by doing this, I got a memo, and then I just need to DFS everybody. Right, so I do this. Well, I should have a list integer res equal to new array list. We actually need this. Right, array list. No. Path equal to DFS node if path dot size is larger than res dot size and res equal to path. We don't do this, and at the end we do res. All right, how about this one? All right, let's go with the easy ones. No, wait, what the hell? We forgot to add. Get node dot add node. Forgot to add this one. Okay. Let's try this. Wow, this one take way too long, man. Yep, that's the one. Each smaller number points to a bigger number that divides it. Then we use DP. Use DFS and DP to traverse the graph and find one of the find the longest path starting at each node. The answer is W here is the longest path among these longest paths, if you know what I mean. Right? Okay, so this one, come on, this one, give it to me, give it to me, give it to me. It does, but it's kind of slow though, kind of slow. Can we do better? Right? Can we do better? We probably can. Hold on. How many have we? Oh, okay. We maybe can do better. Let's see. How can we check if we can do better? Visited? Do you want to try visited? But is it the same as a visited? Because if you visited, it's already been visited, right? So it won't visit again. It will not visit again. You go through all the kids, right? And from here, it will go, 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 go. Eventually, it will go to something. So I have the path. I have the path. I have the path, right? And then if it handles on the other side, so I don't have to go through. I don't know, man. Do we have a better solution than this? Take a look. DFS, standard DP solution. Records the index of the next number that belongs to the same max divisible subcount. Counts the size of the max divisible subset starting from nums. Yeah, we sort, and we do this, and then we DFS. What the hell is this? Oh. Oh, okay. I see. I see what they're trying to do. So we don't do this part. I like to do this part though. I like to do this part. That's okay. All right. Okay, this is a count. Count is 0. Then I go through the remainder. We try to see if it's this or DFS. And then if count is larger than, then count starting from here is equal to this. Post. I see. You use this to grab where it's supposed to point to. Use this to grab where it's supposed to point to. And count plus equal 1. Interesting. Very interesting. And now we go through everything, and then index is the max of the count. Okay, max count. We do the index. Then we find starting from where, right? Starting from max count records the size of the max divisible sub starting from nums I. Okay, starting from nums I. I don't think it starts from nums I. No, starts from I, right? And now we have the index. So we know that's one of them, right? And then we kind of decrease rest of append index. Yep, that is a good solution. Yeah, that's right, that solution. Oh, that don't take so long. I was thinking about doing 2 today, but turns out we only have capacity for 1, unfortunately. All right, let's do this, J. All right, so this is the solution from 2021, 11/15. It is the same. Well, I shouldn't say it. It has basically the same idea, okay? But the implementation is different, right? It's different, and most likely faster. All right, anyway, so let's do this. So we're gonna do, so we will have int count equals to new int n count I records the size of the largest divisible subset starting from nums I. That's true, starting from nums I. All right, so this is not gonna work. So we're gonna say this. Oh, oopsie doozy. See this. Okay, and then we're gonna go p, and let's do this. Okay, so that's that. Oh, and arrays dot sort nums. All right, so int post, right? Post or pre. So we say post I records the next, right? The next value in the path. The next value in the path for the largest divisible subset. The next value in the path, the largest after nums I. Okay. So I have all that. Then I can do probably gonna do it here. Private void DFS. Have a node. Don't return anything. Yeah, these probably need to be above. Okay. Okay, so we have all that, and the minimum is 1, so we can say if count node is equal to 0, right? Which means we haven't visited yet. If count node is equal to 0, which means we have not visited yet, then we need to visit it, right? And if it's larger than 0, then we have visited this count already, right? Yeah, okay, so if count is 0, then what we need to do is, oopsie doozy, I also need, that's fine, let's just pass in nums, it's okay. Then I just say for, oh, node, we probably shouldn't do node. We probably should do index. Okay, they're all index. Okay, they're all index. Then for I equal to index plus 1, I smaller than nums dot length, I plus plus. I just realized we don't have this n. Okay, we don't have. You know what? That is not right. Oh, no. Oh. What the hell did you do? Undo. All right, let's go to 37J. Let's just do this. And do this. We say count was new int nums.length post new int nums.length. Okay. Okay, now here we can do right. What do? We for I is if right nums I let's say mod nums index is equal to 0. Right, that's something we can do. Then we say DFS I nums. Okay, and we say if count if count index, actually we should say if count I is larger than count index, then count index is equal to count I and post index is equal to I, right? Yeah, and then we go through this blah blah blah. Once we finish, count index plus plus, right? This is to add the current node. So we do DFS. So we say for int I 0I smaller than length I plus plus. We just simply do DFS I and nums. Okay. Once we're done with all that, we say list integer res equals new array list. Redo. Redo. Wait, hold on. Undo. Undo. Okay, let's do this. List integer res equals new array list. Okay. Then we need to find out the largest of, so int index, okay, equal to, how do I find a maximum? I probably have to write it myself. Int index equal to 0. And then for int I 0I smaller than nums. You know what? I shall do it here, right? We can say int max count, right? And then we simply say, DFS I nums, that's fine. And max count int max count index, okay, equal to 0. And we simply say if count I is larger than max count, and max count equal to count I, and index equal to I. So once we're done with that, we have I. Then we'll do this res, and we have the index. And we say res dot add nums index, right? So that's the 1, right? That's the 1. Yeah, because post index was, and we just say while index, because index will be while nums index. Wait, hold a second. So count index, right? count index starting from here is the biggest, and then we say, okay, starting from here will be this, right? And next one is big, starting one there. So okay, so this index is the small, because you go small to big, right? So therefore we shall say while index, for a second, while index is so we get a next one, we get a next one, until we go to the next one, which, oh yeah, which doesn't have any, right? So someone will never have, so it still be 0. Yes, that's right. So while index is larger than 0, okay, then we say rest.add index first, and index shall equal to post index. So once we've done that, we're going to return res. Okay, so let's try this 47k. All right, let's see this one, right? Forgot the int. You gotta be kidding me. That was bad. That was very bad. Okay. Nothing gets returned. Huh. Okay, let's debug. I'll do DFS I and nums. Okay, that's fine. And we say if count index equal to 0, which means I have never done that yet, then I'll go through the remaining of the numbers and try to check if I is divisible. If it is, I'll do DFS on that, right? I'll do DFS on that, and after that I'll get the count, right? I'll get the count, and once I get the count, I'll check, right, the current count, which is the index. If this one I count I is larger than, now we do that, and I'll set the post. And then once we go through everything, all the i's, right? Once we go through all the i's, then I jump out and my count index will be plus plus. Okay, that seems innocent enough. And then we go through this thing, right? We find the max count, we do DFSI. Okay, we do DFSI. So DFSI shall tell us the max count starting from I, right? And then we say if count I is larger than, then max count equal to count I, and then index equal to I. So we go through this, we should get the index, right? Or get the index. Ooh, index might be 0. Holy crap. Holy crap. How are we going to do that? Okay, I can do that like this. Res.add nums, and it's also not adding index, it's adding nums index. My god. Okay, and index equal to post index. Then we can say, well, this, then I add nums. Okay, try this. Yeah, this one's right, because the starting index the starting index might be 0, Do they have do while? I'm not sure. Do? While? I have never used do while in my life. Okay, maybe I need this. I have no clue. Never used do while in my life. No, shit. There is do while. Holy crap. Oh, wasn't most like, it's like twice as fast. Twice as fast, man. Twice as fast. Mainly because we don't have to deal with all the data structures. There's no data structure in this one. Alright. That's now undo. Yeah, didn't expect it to take that long, but good learning experience. Alright, that will be it, guys. I will see you guys tomorrow. Adios.